Welcome to The Explainer. Today, we are taking a hypothetical journey to one of the most mysterious, most powerful objects in the entire universe. But hey, this isn't science fiction.
I mean, forget what you've seen in the movies. We're going to look at the real physics of what would happen to you as you approach and then cross this ultimate point of no return. Okay, so before we get anywhere near the main event, let's start from a safe distance and just get one of the biggest misconceptions about these things out of the way right now. You hear it all the time, right? That black holes suck everything in like some kind of cosmic vacuum cleaner. But they don't. Seriously. If we magically swapped our sun for a black hole with the exact same mass, you know what would happen to Earth's orbit? Absolutely nothing. We just keep going around like nothing changed. See, from a distance, gravity is just gravity. The real danger isn't being sucked in. It's about getting way, way too close. So let's say you decide to get closer. You'd eventually cross this invisible line in space. It's called the Innermost Stable Circular Orbit, or ISCO for short. Think of it like this. On the outside of the ISCO, you can chill in a nice, stable orbit forever. But the second you cross that line, whoa, a stable orbit is just not possible anymore. You've got to hit the thrusters and hit them hard just to stop yourself from spiraling in. And if you can't fire those engines, well, you're in for a rough ride. You're going to join something called the accretion disk. And trust me, this is not a place you want to be. It's this insane, swirling vortex of superheated gas, dust, and shredded stars. All that stuff is rubbing together as it spirals down, and the friction heats it up to millions of degrees. It's blasting out a storm of deadly X-rays and gamma rays. It is, no joke, one of the most violent places in the entire universe. Okay, but let's just pretend for a second you've got some kind of indestructible spaceship, right? You've somehow survived the chaos of the accretion disk. Now, you're getting close to the most famous and, frankly, the most bizarre feature of a black hole. And there it is, the event horizon. Now, this isn't a physical wall or a surface you could touch. Think of it more like an information firewall. It's the point where gravity gets so ridiculously strong that the speed you'd need to escape is faster than the speed of light itself. And since nothing can go faster than light, nothing, not even a beam from your flashlight, can ever get back out. So, the big question, right? What actually happens when you cross it? And this is where things just get mind-bendingly weird. Because the answer, believe it or not, completely depends on your point of view. It depends on whether you're the one falling in, or if you're me, watching you from a safe distance. Okay, get ready for a paradox. From where I'm standing, way back here, as you get closer to the event horizon, it would look like your clock is slowing down. Time itself for you would seem to grind to a halt. I'd see your image just freeze, right at the edge, getting redder and dimmer until you fade away, forever. But for you, in your spaceship, your watch ticks completely normally. You wouldn't feel a thing as you sail right across that boundary. For you, it's over in an instant. It's like two totally different realities are happening at the exact same time. Now, just because you might not feel yourself crossing the horizon doesn't mean your journey is going to be a pleasant one. Oh no. You still have to deal with a process that physicists gave this just wonderfully graphic name, spaghettification. And whether you get turned into cosmic spaghetti really depends on one thing, the size of the black hole. If you're falling into a small, stellar mass one, the tidal forces are just immense. The pull of gravity on your feet would be so much stronger than the pull on your head that you'd be stretched into a thin noodle of atoms before you even reached the event horizon. Game over. But if you're falling into a supermassive black hole, the kind at the center of galaxies, the event horizon is so huge, the curve of spacetime is so gentle that the tidal forces are actually pretty weak. You could literally drift right across it, completely unharmed, without even realizing you just passed the point of no return. All right, so everything we've talked about so far, that's for the simple kind of black hole. But the real universe, as you can probably guess, is a whole lot weirder. Because black holes don't just sit there. Yeah, they spin. The very first idea of a black hole, figured out by Carl Schwarzschild way back in 1915, was for a perfect, non-spinning sphere. It's a great starting point, but it's a bit of a mathematical fantasy. It took until 1963 for another physicist, Roy Kerr, to crack the equations for a spinning black hole. And that's what we actually think is out there in the cosmos. So this chart basically lays out the whole family of theoretical black holes. You've got two main properties, charge and spin. Now, charged black holes are probably just theoretical. They're not likely to exist. But that one in the bottom right, the spinning, uncharged one, that's the Kerr black hole. That's the one we expect to find in nature. It's the engine that powers quasars and shapes entire galaxies. So, a spinning black hole does more than just bend space-time like a bowling ball on a trampoline. It actually drags space-time around with it. It twists it. The analogy here is perfect. Imagine a spinning ball plunged into a thick vat of honey. You see how the honey right next to the ball gets swirled around? A spinning black hole does that to the very fabric of reality. It's an effect called frame dragging. And this frame dragging effect is so unbelievably powerful that it creates this whole new, bizarre region outside the event horizon, a place called the ergosphere. Okay, so inside the ergosphere, things get wild. You are still outside the point of no return, so technically you can still escape. But, and this is a big but, it is physically impossible to stand still. Space-time itself is swirling so fast, it just grabs you and forces you to spin along with the black hole. You have no choice. In fact, scientists have theorized you could even use this effect to steal a bit of energy from the black hole's spin, which is just an incredible idea. So what happens if you survive all that? You go through the ergosphere and then you finally cross the event horizon of a spinning black hole. Well, this is where the predictions of general relativity go completely off the deep end. You see, inside a simple, non-spinning black hole, everything crushes down to a single point of infinite density, the singularity. But inside a spinning Kerr black hole, that rotation, well, it flings the singularity outward, smearing it into a one-dimensional ring. And this ring is where the math just gets wild. According to the equations, if you could somehow pilot your ship perfectly, you could pass right through the center of that ring, and you wouldn't be crushed into nothing. No, the math suggests you could enter a whole new theoretical region of spacetime, maybe even a new universe. Now, to be clear, pretty much every physicist thinks this is incredibly unstable and would collapse in a flash, but the fact that the possibility even exists in the math is just mind-blowing. And that leaves us with one final, absolutely fascinating question. Let's forget about diving in for a second. What if we could just harness that bizarre region on the outside, the ergosphere? Could a far future civilization actually build some kind of megastructure around a spinning black hole to tap into its immense rotational energy? Could we turn these cosmic monsters into the ultimate power plants? It's a staggering thought, and a pretty wild place to end our journey.